calculating entropy changes. So this is where we start to get quantitative. So what is the value of the entropy change for a given reaction? So we're now going to be dealing with entropy quantitatively. So we're looking at actual sizes of entropy changes. So here we go. Two important properties of entropy. First one, I want you just to flip back to the graph that you sketched and notice something, which is that the entropy starts here at 0. So when we're here at the temperature, this is absolute temperature, so we're talking about 0 Kelvin. When we get down to 0 Kelvin, entropy is 0 for a pure substance. You've got a mixture, you may well have some entropy there because you've got some disorder because they're not all perfectly mixed together. But when you've got a pure substance, just one thing, it's not going to have any entropy when you reach absolute 0. So if we go back to this, so entropy is 0 at a temperature of 0 Kelvin. This is say because particles are not moving, have no energy. So when the particles have got absolutely no energy, they can't have any entropy. They're not moving, there's no way to spread the energy around, and therefore it's not going to have any entropy. So think about it in terms of money. If you don't have any money, there's no choice about what to spend it on. So why is that really useful? Well, that's incredibly useful to us because what it means is that we can determine the absolute entropy of a substance. Each substance has an entropy value. So you can say to me, well, what's the entropy of water? And I can say, well, it would be this. If you ask me what the enthalpy of water is, I can't tell you because enthalpy is not necessarily 0 at a temperature of 0 Kelvin. It depends on the bonds and the actual atoms that are involved. Entropy, because it's essentially a sort of statistical thing about how you spread energy about, you can say entropy is 0 at 0 Kelvin. Okay, second point that's worth us noting down is that the entropy is directly proportional to the amount of substance. And that is so helpful. The original definition of entropy was basically making that to be the case. So the great thing about that is if I know the entropy of 1 mole of a substance, I can work out the entropy of 2 moles, etc. So that's great. Directly proportional to amount of substance. We'll see that coming in handy in just a second. So what we tend to work with is these things called standard molar entropies. And they are, the units of the standard molar entropy is joules per Kelvin per mole. So that's our standard conditions. standard conditions is usually a temperature of 298 Kelvin, but do check that in the textbook. I can't remember exactly off the top of my head, but I'm pretty sure the standard condition is usually 298 Kelvin. And the wonderful thing about all standard molar entropies is they're always positive. You can't have negative entropy. 0 is the lowest value you can possibly have. So unlike, let's say you were looking up an enthalpy of formation or something like that, it could be positive or it could be negative. Entropy is dead easy because they're always positive. That doesn't mean entropy changes can't be negative, but the entropy itself is always positive. So that is the nub of entropy. And essentially, the standard molar entropies are tabulated in data books. Or perhaps you're more interested in exam papers. So you don't need to know. You don't need to know what the entropy of water is. It'll just tell you if you need it. Right, let's move on to a concrete example as we come to a finish. So this is how you're going to calculate the entropy change in a given situation. It's very straightforward. The standard entropy change is the sum. That's what this funny symbol here means if you're not used to that symbol. It just means the sum of. So the sum of entropies of the products minus the sum of the entropies of the reactants. And I've just put the Plimsoll symbol there just to show I'm dealing with standard entropies. It would work under non-standard conditions as long as you chose the same non-standard conditions for all of your entropies. So the standard entropy change is the sum over the product's entropies minus the sum over the reactant's entropies. So here is an example to get you to grips with that formula. So here is the worked answer. So we're going to work out the entropy of the reactants, and what I would do if I were doing this was that I would actually write this directly beneath the substances underneath. So I'd write for my reactants 172.8, and then I would note my 3 moles of hydrogen. So that's where the fact that 1 mole is 130.6, direct proportion means 3 moles. You just times it by 3. And then the products, that's the entropy of the products. And then we just got to make sure we do products minus reactants. So 204.4 minus 564.6 and minus 360.2. And I'll just give you a very quick note here that we make sure that we keep the lowest number of decimal places from the data given. So this is one of those relatively rare situations where you are actually conserving decimal places, and that's because you are fundamentally adding and subtracting here. So you need to keep the same number of decimal places. You're only multiplying by a number that you know to infinite precision, so you don't need to conserve significant figures here. You know it's exactly 3 moles of hydrogen. Right, we are almost there. So remember, the main question that we're trying to answer in this topic is, how can you decide whether a process will be feasible or not? Now, what we've done in this topic, this sort of little section on entropy, is that a system becomes more stable when its energy is spread out in a more disordered state. So in a feasible process, entropy should always increase. And that is known as the second law of thermodynamics. Second law of thermodynamics. Probably one of the most fundamental laws in all of physics and chemistry. So in a feasible process, entropy should go up because the system becomes more stable when energy is more spread out. So entropy should go up. The only problem is, in this case, the entropy goes down, and that reaction is actually a feasible reaction. So we have a bit of a problem here, but there are feasible reactions. Where delta S is negative. So there are feasible reactions when delta S is negative. So we have a problem. In terms of how can you decide whether a reaction is going to be feasible or not, we can't use delta H alone. We found out, as useful as entropy is, and as much as you'll have to answer questions on it in your exam, and as much as the second law of thermodynamics does state that entropy should always increase, you can't predict just from delta S alone whether a process will be feasible or not. And if you're feeling really confused and frustrated at this point, then that's exactly where I hope I've led you to. You should be able to work out what entropy is qualitatively and quantitatively. But if you're thinking, well, how can you decide whether a process is feasible or not at this point? Then you're teed up perfectly for what will come next week.